Okay, any questions before we continue? So let's continue how these relativistic corrections will change the other laws. We already have seen how the Newton's second law should change. Well, it's just a slight modification. The only thing is that we write it in terms of the momentum, and we use the relativistic expression for momentum in the second law. Now let's look at how we define the energy. Again, if you go back to your mechanics courses last semester, to define the energy, what you did was you first defined the kinetic energy. Well, in Newtonian dynamics, you had the kinetic energy was equal to, well, you had the F dot dl. This was the change in the kinetic energy of the object, and it turned out to be 1 over 2 mv squared v final squared minus 1 over 2 mv squared v initial squared. Basically, we will do the same thing. We will start with this definition of the change in the kinetic energy, but this time we will not use the Newtonian expression, but the corrected expression. So the change in the kinetic energy of the object will be F dot dl as my object goes from point A to point B. Now the force acting on the object is dp divided by dt, scalar product with dl. Well, which can also be written as dp by dt multiplied with dl by dt. Let's multiply it also with dt. So the change in the kinetic energy of the object is dp by dt times v times dt. Or if you also like, from t0, t initial to t final. So how would you like to proceed to evaluate this integral? Well, if you want to use the integration by part, let me just write it in this form, dp dot v, which is p dot v from initial to final minus v dot dp.
Shouldn't we convert the limits? Shouldn't we convert the limits from t to v?
Well, that's why I didn't write it down explicitly. Just always understand that the lower limit is the initial value of whatever you are integrating. And now, well, let's avoid integration by parts. It will just make it more complicated. But you see, we already know what P is. P is m times V over 1 minus V squared over C squared. So what is dP? This is m times dV times gamma plus mv times minus 1/2 times gamma cubed times minus 2v dv over c squared. So the change in the kinetic energy of the object can be written as v dot, well, dp is m time, well, let me just take m out, gamma cubed out. Here I have 1 over gamma cube dv plus, where? Oh, here, yes. Plus gamma cube is out, m is out, v dot dv. Yeah, okay, let me make a simplification. Let me just assume everything is one-dimensional. Everything is in the same dimension, so it will just simplify the computation. This is equal to v times m gamma cubed 1 over gamma squared plus v squared dv. And here there is a over c squared. Well, 1 over gamma cubed, there's a c squared over here. This is 1 minus v squared over c squared. So if I just sum them up, this whole parenthesis is 1. So the change in the kinetic energy of the object will be just m times v gamma cubed dv. Well, gamma was 1 over 1 minus v squared over c squared under the square root. d gamma by dv, now I'm taking the derivative with respect to the speed, not the velocity. This will be equal to minus 1/2 because of the square root, 1 over that square root cube times minus 2v over c squared. These cancel, so this is just v times gamma cube over c squared. So the change in the kinetic energy of the object is just m times v times gamma cubed is nothing but c squared times the derivative with respect to v of gamma times dv. So, but this is nothing but m c squared times gamma from the initial to v final. Well, let's assume the object starts from rest. So the change in the kinetic energy of the object is just will be equal to the final kinetic energy of the object, which will be equal to, well, when we put v final, this is mc squared. Well, let me just call this v for simplicity times gamma. When v initial is equal to 0, gamma is just 1, so this is minus mc squared. So the kinetic energy of an object, if it is moving with a speed v, is equal to mc squared gamma minus mc squared. mc squared gamma minus 1. We just use what you have already used in the mechanics course, the work kinetic energy theorem. So the change in the kinetic energy should be always equal to the work done on the system. And for at least since the kinetic, what we understand from kinetic energy is an energy due to the motion of the object. If the object is not moving, then we prefer to define it as having zero kinetic energy. That's why we started from the initial speed is zero, so the initial kinetic energy is zero. Final kinetic energy is whatever its final value is. The change in the kinetic energy of the object is just the final kinetic energy minus zero. And that change, using the work energy theorem, just turns out to be this expression over here. Now, what about the energy of the system? Because in mechanics, you define the energy of the system as the kinetic energy plus the potential energy. Well, here there's no potential energy, except then maybe some energy of the object due to its existence. Not due to its speed, but its existence. So if there's no potential energy to change, so the change in the kinetic energy of the object is nothing but the change in the energy of the object, the total energy. So the energy of the object, the final energy, is the initial energy plus mc squared times gamma minus 1. This is all we can say without any ambiguity. Since there is no potential energy, the change in the kinetic energy is the change in the energy, while the change in the energy of the object is just E final minus E initial. The change in the kinetic energy, we had calculated it to have this value. E final is equal to mc squared times gamma plus E initial minus mc squared. And we just define this quantity. You see, that's just a constant. This is the energy of my particle when it is at rest. Well, this is some constant. So I can just choose this constant to be 0. But if I choose that constant to be 0, the energy of the object is just mc squared gamma. Well, in a sense, this is a definition. Just like, you see, when we are talking about the potential energy, we always say that we cannot determine the value of the potential energy. We can only determine the changes in the potential energy. The same thing more or less holds here. We cannot really determine the absolute value of the energy, but we can just fix a scale. We say that the energy of the object, and it's this constant over here. It's a choice, it's a definition. We just define this constant so that this combination is 0 and the energy is just mc squared gamma. Well, if this is, and it turns out to be also valid if you see, here the particles are not changing into other particles. But if the particles were to change into other particles, for example, in accelerators, we can just have photons, or the electrons, let's say, which have a very small mass. They collide, and after the collision, we end up having protons, which are 2,000 times heavier than the electrons. So what actually happens is the energy of the electron, the kinetic energy of the electron, is converted into the mass of the protons. And to avoid many constants appearing over here and over there, that choice seems to be the most convenient. So, what is the mass? Of a system? Well, you see, the definition of the mass in first year was Newton's second law. So there is a force. If you exert a force on the object, it will accelerate, and the force and the acceleration will be proportional to each other, and the proportionality constant will be the mass, the inverse mass. But in that interpretation of Newton's second law doesn't hold anymore, that definition of the mass, because the force now is not in the direction of acceleration. But this definition of the energy kind of gives us a different definition of the mass of an object. The mass of an object or a system of objects is the minimum energy the object can have. Well, this also applies to systems like the proton. You see, the proton is not just a single particle. It's a collection of quarks and gluons and many subatomic particles. So what is the mass of the proton? Well, it is the minimum energy that all those quarks and gluons, etc., can have in that compact object. And that minimum energy, in fact, turns out to be much higher than the sum of the masses. You see, this definition of the mass is not just saying that the mass of an object is the sum of the masses of the objects making the system. It's more than that. Now, we will see when we discuss quantum physics that if you confine objects to a very small volume, like the proton, the objects cannot have zero kinetic energy. They have to have some finite kinetic energy, and that finite kinetic energy contributes to the mass of the object. So in this sense, the mass and energy are basically the same thing. Its mass is nothing but the minimum energy that the system can have. Now, back to other questions, though. What about gravitational mass? Some of you were asking if we will be discussing massless particles. If particles do not have mass, how do they feel the gravity? Well, the particles do not feel gravity through their mass. They feel gravity through their energy. Everything that has an energy creates a gravitational attraction and is influenced by gravity.
Can we make the time for the mass definition to photons or light? Can we do some definition for the mass of photons or light?
What do you mean? For example, this definition, in this definition, what is the minimum energy of the photon or light? The minimum energy of photon turns out to be 0. And hence, photon doesn't have any mass. You can create photons of arbitrarily small energy. So it doesn't have a mass. Well, let's see what about momentum if that is the case. Now, so these are the questions we will be answering. What is the relation between energy and momentum? Again, what is the relation between v, the speed? How can we write the speed? Well, I mean, in the case of massive objects in Newtonian dynamics, you wrote the velocity of an object as its momentum divided by the mass. But that definition obviously doesn't hold for particles that might not have mass. So how can we generalize it? So let's see. We have the momentum. We define the momentum as gamma m times v. Then we have the energy, which is gamma m c squared. Well, let me start with taking the momentum squared. Well, momentum squared is gamma squared m times v squared. Or before looking at that, let me look at something else. let me just divide P by E. Well, if I divide P by E, it's nice because these gammas cancel, M's factors cancel. So I obtain V over C squared, which tells me that I can obtain the velocity of an object from the momentum by dividing its momentum by E over C squared. In most applications, in most Newtonian applications where you have a mass m, you would get an almost correct answer if you replace that mass m by E over C squared. You see here, this definition of the velocity in terms of momentum is just momentum divided by the analog of mass, E over C squared. And in fact, if the particle is not moving at very high speeds to a very high accuracy, this is just mass squared. This is just the mass of the object. Because you see, E is gamma m times C squared. If the speed of the object is very small compared to the speed of light, then gamma is just 1 to a very high accuracy. If gamma is 1, E over C squared is just m. Well, let's see, what is the unit of energy? Kilogram meter squared per second squared. What is the unit of C squared?
Mass enerji ise kilogram hani bir enerji birimi değil ya şey olarak dimension olarak biraz tuhaf kaçıyor diyorsun.
You see, kilometers and meters. They are both length units. They have different units though. How do you convert one to the other one? Well, multiply by 1,000. 1,000 meters per kilometers. So you have this conversion unit. 1,000 meters per kilometers. So this is just you see, if you have some quantity, let's say 500 kilometers, you just multiply it with this factor, this conversion factor, and you obtain 500,000 meters. Energy and mass. We are saying that they are both energy. They are both correspond to energy. And there is a conversion factor, which is C squared. C squared in this sense is just a conversion factor. Now let's look at something else. Let me just write down the result. Let's look at E squared over C squared minus P squared. Well, on one hand, E squared is gamma m C squared squared over C squared minus gamma m V squared. Well, let's see, they both have gamma squared, they both have m squared. The first factor has c to the 4 divided by c squared. The second factor has v squared. This is gamma squared, m squared. Let me take out a factor c squared also. 1 minus v squared over c squared. But this is nothing but 1 over gamma squared. So this factor cancels this one. Well, you see, the energy, is it invariant as we go from one reference frame to the other reference frame? Will it have the same value, or will it have different values in different reference frames? It's invariant. Who thinks it's invariant?
What is it?
Energy. Is it invariant as I go from one reference frame to the other reference frame? Will it have the same value in every reference frame? Why or why not?
This equation shows
E, this equation, how does it show that E is invariant?
because we use it's not important what how we choose reference frames. If we plot the correct values, we should have find same E value.
Well, you see, this equation is invariant. So in the sense that whatever you measure for E, whatever you measure for the momentum of the object, if you put it over here, you should get m squared. C squared, m is just the minimum value of its energy. The minimum value of the energy of a particle is the same in every reference frame. So this is an invariant quantity. Mass doesn't change from observer to observer. So whatever you measure for E, whatever you measure for the momentum, if you put it over here, no matter which observer you are, you should get the same value. But that doesn't tell me that E and P separately, they should be invariant. It just tells me that this difference should be invariant.
I don't think the values of the momentum and energy, they are invariant.
So what do you mean you don't think? What's your proof?
Yeah, there's conservation of momentum and energy in in all reference frames.
Okay.
That's true, but how can I don't know how to prove it.
Well, let's see. How do you calculate the energy of an object?
Using the formulas?
Well, yes. How do you use the formulas? M is, we said that it doesn't change from reference frame to reference frame. C doesn't change from reference frame to reference frame. That was the starting point of special theory of relativity. Gamma? Gamma is a function of the velocity of the speed of the object. But the speed of an object depends on which reference frame you are using to measure it. So gamma changes from reference frame to reference frame. So energy will have different values for different observers. But whatever the observer is, E changes from observer to observer, P changes from observer to observer, but as your friend had pointed out, this combination does not change from observer to observer. It's always the same for every observer. Just like, you see, if you remember, we had looked at C times delta T squared minus delta R squared. This is also invariant. You see, different observers will measure different time between two events. They will measure the events to happen at different distances from each other, but this combination will always be the same for every observer. Just like that, energy and momentum of a particle can be different from observer to observer, but nevertheless, for every observer, this combination will always be the same.
Mass'in relativistik olduğunu kabul edip bir equation derive etseydik yani momentumun korunumundan gelen bir sonuç olarak orada da aynı şey mi çıkacaktı? Hani mass değişiyor gibi görseydik.
Well, you see, this mass over here, if you were to define some relativistic mass, which you should not, I mean, if you ask anybody who is doing physics, whether the mass changes as the speed of the object changes, the answer is always no. The mass doesn't change. It's a constant. It's a property of the particle or the system. So here what would happen would be m0, which is sometimes defined as the rest mass. It is the mass of the object in the reference frame in which it is at rest. So whatever reference frame you have, the mass of the object is always defined like that. You just go to the reference frame in which the object is at rest. So the momentum is 0. You measure the energy of the object in that reference frame, and then you just divide the energy by c squared to get the mass of the object. Now let's come back to the question of massless particles. You see, for massless particles, these expressions do not make any sense, assuming gamma is finite. M is 0. But if gamma were infinite, well, you have an uncertainty over there which you have to resolve somehow. Mass times the mass times gamma, it will be 0 times infinity, which is uncertain. It can have any value, so we have to use some other means to determine the value of the energy and the momentum of the particle. So basically, this is one argument that says that if there are massless particles, for them to exist, for a particle, existence means mainly it has an energy and momentum. For a massless particle to exist, it has to move at the speed of light to make gamma infinite. Now let's look at how these other expressions lead us to the same result. If m is equal to 0, well, in that case, we know that E squared over C squared should be equal to P squared, or E should be equal to P times C. So if there is a massless particle, then its energy and momentum are should be related through such a relationship. Now, what about its speed? We argued that by claiming that these expressions should make sense, so that gamma should be infinite, and hence the speed of the object should be equal to c. Well, we can also look at the definition of the speed, the velocity of the object. The velocity of an object is defined as, can be determined as the momentum of the object divided by E over c squared. Well, this is equal to P over E is P times C over C. No, C squared, no, C over C squared. This cancels one of them. So this is P, no, this is P over P multiplied by C, or C times P hat. So the speed of an object that is massless, the velocity of an object that is massless, is in the direction of its momentum with a magnitude always given by c. You see, since this object always moves at the same speed c, its momentum cannot be determined from its speed only. Its momentum has to be given by some other properties of the system. Like in the case of electromagnetic waves or photon has some other properties like the wavelength. The momentum of the photon should be determined somehow by its wavelength, which for the time being we don't know how they are related. But at least principally, there is no reason in special theory for a particle to have a mass. Massless particles are possible. But the only constraint is that they have to move at the speed c. So you see, this already tells us that the speed c is not something special to light. C is just some fundamental property of nature, some fundamental speed defined in nature, that every object that is massless has to move at that speed c. So that is why calling c as the speed of light from this point on doesn't really have too much meaning. It just tells us that the photon is massless. But any object that is massless has to move with the speed c. Now, I'm stressing this to avoid the confusion about what happens in medium. The speed of light the speed of light in medium is slower, so should we replace c with that slower speed of light? Well, basically no, because c, as I am stressing over here, is not necessarily the speed of light. It is the speed of fundamental speed found in the laws of nature. Why does nature have such a fundamental speed? We don't know. It seems it just has. Any questions on massless objects, energy? Well, first question, does it make sense to define a kinetic energy over there? You see, how did we define the kinetic energy? We said that the object has a rest mass, rest energy, and the difference of its total energy from its rest energy is what we call the kinetic energy. Now, the first question, does there exist a reference frame in which the photon is at rest? There is no such reference frame. So the photon can never be at rest. It is always moving with the speed c. So how do you identify this kinetic energy? Well, this is one point of view. Another point of view, you can say, well, the minimum energy that the photon can have, I claim to be 0. So all the energy it has is due to its motion. So this E appearing over here is actually the kinetic energy. But at the end of the day, it doesn't really make any difference in practical applications. Yeah, one application will be, in most applications, you will be using the conservation of energy, not the kinetic energy anyway. Well, the velocity has a direction. Momentum also has a direction. Well, we had already said from the beginning that the momentum of an object, we are defining it to be in the direction of the velocity of the object. So it's just consistent with our previous definitions.
Massless bir partikülün momentumu nasıl olabilir? Yani bir yönü olması için önce bir varlığından dolayı inersi olması.
Why? Why should it be so? You see, the photon is not accelerated. Well, if it changes direction, it is accelerated, but one of you were asking, if you create the photon, doesn't it start from rest and accelerate to the speed of light? No. It is created at the speed of light. You see, most of our notions of momentum is based on massive objects. That is what's kind of causing the confusion. And massive objects can be at rest. But photon is massless, so it cannot be at rest. There was a question over there.
So using Newtonian mechanics, I guess we explain reflection, for example, as something without interaction with the mirror. Like it doesn't absorb it, something like that. So how about
Well, okay, so some of this you will study in more detail next semester when you study electromagnetic theory. You see, for example, why does the photon slow down in medium? Well, essentially, it does not. What happens in medium, what you call a medium, you can define it as just some dots, some point charges here and there. So these charges, what they will do is they will just scatter the photon. There's a charge over here, the photon will come over here, so it will scatter and move in that direction, and then scatter from here and move in this direction. So on the average, the photon will just move a zigzag motion. On its average speed will be less than c. But if you would just look at measure the speed of the photon between two scatterers, it will between those two scatterers, it will still move at the speed of light, c. Does the photon accelerate? I will now say yes, it does accelerate. You see, acceleration can be caused by two things. It can be caused by the change in the velocity, change in the speed, or it can also be caused by the change in the direction. So the photon can change its direction. Well, one thing is in medium, you can say that, okay, it's changing direction in diffraction and refraction. It's changing direction. But that you can also argue that it's being absorbed and re-emitted, etc. So that doesn't really count like acceleration. But then it also accelerates as it's going near the sun, because it feels the gravitational force. Then we come to the next question. How come the photon feels the gravitational force if it is massless? So Newton tells us that the gravitational force is proportional to the mass. If you have two objects, it's the product of the masses. How come the photon feels a force? But you see, just like over here, E over c squared, it acts like the mass in Newtonian dynamics. Well, what creates gravitational force and what feels the gravitational force, it turns out to be the energy, not the mass. So since the photon has a mass, it does feel the gravity. Since the photon has an energy, even though it doesn't have a mass, it does feel the gravitational force. In fact, if you use E over c squared as the photon mass, you get almost correct results for how much the beam bends as it goes around close to the sun. You will be missing just a couple of factors, like 2. Well, you see, what does it mean to bend? Here is the sun, the photon comes and it just moves in that direction after passing through the sun. So this is the initial momentum. This is the final momentum. Its momentum changes. This is the initial velocity with the speed c. This is the final velocity with the speed c. So initial velocity and final velocity are different. So that means it's at accelerator. Because acceleration just means change of velocity. Although its speed is constant, its velocity is not. Well, we will come to that later on. There's still the question we need to answer. Okay, so if the speed is constant, so energy doesn't change as a function of its speed, like for other particles with mass. Its momentum doesn't change as a function of its speed, like the momentum of massive objects. So what do they depend on? How can we determine the energy and momentum of a photon? How can we express it in terms of maybe some other properties? That will come.
Mesela göre gravitational field tanımlayabiliyoruz. Peki enerjiye göre de tanımlayalım dediyse.
Sure, why not? Define it. Well, I mean, I don't want to go into too much detail in gravity because then we need general theory of relativity. But as just somewhat a rule of thumb, let's say, or somewhat to get an idea, you can replace the mass of any object, whether feeling the gravitational force or creating the gravitational field, by the energy divided by c squared. And you will end up getting results that are decent. Not far off from the exact results. Other questions? Well, you had many questions. We will continue on this topic on Monday. But just to give you an idea. Let's take a simple case. We have this wire. It carries a current I in that direction. It is neutral. Well, what does it mean it is neutral? If you would plot a very simple picture, you have the positive charges at rest, and you also have negative charges moving. More or less, on the average, if you just call this distance, let me call it L plus, and this distance to be L minus, let's call this charge Q plus, this charge Q minus. Q plus over L plus is equal to Q minus over L minus, with a minus sign because they are just the opposite charges. So as the charge density of the positive charges is equal to the charge density of the negative charges. Let's say that these charges, negative charges, are moving with a speed v in that direction. Let me also imagine another charge outside. Again, let's imagine it's moving with the same speed v in the same direction as the negative charges. It will be basically simplify the computation. Now, in this reference frame, the force acting on the charge Q will be Q times, well, let me put a vector sign over there, V cross B. If it is moving, it will feel a force, a magnetic force. If it is not moving, it will not feel a magnetic force. But then we have this question that we will answer next hour. You see, if you have a charge that is more, if you have a charge that's feeling a magnetic force only, if you start, so it will be accelerating because it's feeling a force. If you go to a reference frame in which it is at rest, it will not feel any force, so it will not accelerate. So how come a particle is accelerating in one reference frame and is not accelerating in the other reference frame? So that is the question we will answer on Monday. Any last minute questions?
You know, the charge is relatively invariant. How to prove it?
Well, if you ask me the charge of an electron, I will tell you that it is -1. It's just the number of charges. What we call the charge is actually the number of charge-carrying particles. So that number is just invariant. If you have 2 electrons in one reference frame, you have 2 electrons in the other reference frame. Okay, see you on Monday.